Swayam Prabha. Digital India. Educated India.
Welcome to NPTEL NOC, an introductory course on Point-Set-Topology Part-II, continuing with the study of filters. Today, Module 33, Ultraclosed filters. Filters and ultrafilters on a given set have nothing to do with a particular topology on X, though they control the behavior of all the topologies on X to a large extent, namely via the notion of convergence. Right? Now we shall introduce a subclass of filters which depend on the given topology tau on X. So that is the difference between these filters and ultrafilters and ultra-closed filters. As the name says, that closedness comes because we are referring to a particular topology tau on X. A filter F on X is called a closed filter if it has a base consisting of closed subsets of X. Okay, so I started the topological space, so closed subsets make sense. It is called an ultra-closed filter if it is maximal in the collection of closed filters. Okay, so that is the definition of closed filter and ultra-closed filter. Now, if an ultra filter is closed filter, then it is ultra-closed filter because it is already maximal in the collection of all filters. On the other hand, you start with an ultra-closed filter, this may not be an ultra filter because it is maximal only in a subclass. So there may be larger ultra filters which are not closed. Okay, so this difference you have to keep in mind, that's all. Now let me have some examples. Singleton capital X is always a closed filter because singleton X is always closed in whatever topology you take, okay, with respect to any topology. On the other hand, every filter is a closed filter on a discrete space because every subset is closed also, right? So you can take the filter itself as a base if you like, no problem. So these are some easy examples of closed filters. The cofinite filter on an infinite set is not a closed filter. Okay, for if it were, then it would contain a non-empty finite subset because the only non-empty closed subsets, right, are the whole space or the finite subsets, right? So if it contains X as a base, then there is no then it has to be, if X is a base, then X is the only element. If it is not, if it is the cofinite filter, X cannot be a base, right? So it must have finite closed subset as a base, but the moment it is non-empty finite subset, okay, that is a contradiction because its complement will be also there as a member. All the open subsets are here, non-empty open subsets are here. That is not possible. Okay, so conclusion is that this cofinite filter, which consists of all open subsets other than the empty set in the cofinite topology, is not a closed filter. So I have given you both examples, easy examples of closed filters as well as not closed filters. Okay, let X be a T1 space. Then I can give you more examples. For each x belonging to X, consider the ultra filter fx. Singleton X being a base for it and singleton X is closed, this fx is a ultra, it's a closed filter. Already it's ultra filter, therefore it must be ultra closed filter. Also note that fx converges to X and X alone. Why? Because fx contains an X. Alright. So these are the important ones and easily available ultra closed filters. Of course, you may expect that there are and there may be many other ultra closed filters on an infinite set. Okay. Every closed filter is contained in an ultra closed filter. So this is similar to every filter is contained in ultra filter. Of course, again the proof is John's lemma. You have to verify something. The verification is very easy here also. The proof is as usual appealing to John's lemma. Take A to be the collection of all closed filters containing a given filter. Automatically it is non-empty. If lambda is a chain inside this family A, each element of this chain has a closed base Bi. Bi is a closed base for Fi. Fi is a chain. Okay. Then take the union of all the members of all the elements in Bi's. So union of all Bi's. That family will be a closed base for union of Fi's. So this is what you have to verify. Okay, because it's a chain, this is possible. Okay. Again, union of Fi is a filter is easy, just like in the earlier case. So it is a closed filter. Therefore, it is a member of lambda, member of this A, and it is an upper bound for all members of this one. So that means condition for John's lemma is satisfied. Therefore, conclusion of John's lemma says that there are maximal elements. So every filter is contained in an ultra closed filter. Ultra closed filter. Okay. Similar to the theorem 5.7.52, which is nothing but characterization of ultra filters. The three characterization we had given. Okay, we have the following characterization. It's not so strong, a little weaker because we have only two of them here. Okay, A and B. Exactly similar, F is an ultra closed filter. The second one is not arbitrary subset but only for open subsets. Every open subset U in X, either U or U complement must be inside F. If this condition is satisfied, it must be ultra closed filter. Start with a closed filter, of course. You don't prove that it's closed filter. Only ultraness is proved. Okay, the proof is more or less same, but you have to see why the openness is coming here. This condition is obviously the weaker condition. It is not for every open set, right? After all, it is maximality is also inside the family of closed filters. So that is the trick. So let us see. Let us go through the proof correctly. A implies B is not very easy. Not very difficult. Start with a closed filter, ultra closed filter. Let B be a base for that. B consists of only closed subsets and it is a base for F. That is the meaning. Given an open subset U of X, consider the family B union complement of U. That's a closed set. So it's a closed family, right? Family of closed subsets, right? If F union U complement has finite intersection property, in fact, you don't need the whole of F. If B union F, this is finite property is enough, then B union UC also has finite intersection property. So these are actually if and only if, and hence it would generate a closed filter F prime containing F. Okay. The moment you assume this has a finite intersection property, there will be a filter F prime that will contain this F because it contains B. Okay. Now F is ultra closed, therefore F must be F prime, which just means that U complement is in F. Okay. If it is not the case, means what? This thing A it doesn't have a finite intersection property. Then what happens? That is, otherwise there exists an A inside F such that A intersection U complement is empty. Okay, that is the finite intersection property is violated. This just means that A is contained inside U. Therefore, if A is inside F, so U is also inside F. So either U is there or U complement is there is what we have proved. Okay, so B is proved now. Now let us prove B implies A. Okay, suppose there is a closed filter F prime such that F is contained inside F prime. We want to show that F is equal to F prime. Let B prime be a family of closed sets forming a base for F prime. Okay, there is one because F prime is a closed filter. For any B inside B prime, suppose this B is not in F. Okay, I am just supposing this is not in F. Then the complement of B must be in F by condition B. But F is contained in F prime. So B complement is in F prime. B and B complement both are in F prime. That's a contradiction, because intersection will be in F prime. Therefore, this B must be inside F. Since this is true for all B, this B prime, the curly B prime, must be inside F. Okay. But B prime generates F prime, so F prime is inside F. So therefore equality holds. Okay. So the proof is more or less the same, but the flavor is different because we have to use the openness and closeness and so on here. That's all. But condition C is missing here. Okay. See, now you understand why last time we put this condition at the last. Okay. And then proved A implies C, C implies B, and B implies A. This condition is nothing but given A union B inside F, A is there or B is there in the case of ultra filters. Now similar condition but slightly different can be expected, but no, this is only one way implication is there. Okay, the corresponding condition C is not equivalent to being ultra closed filter. So let me state it separately, don't get confused with the earlier theorem. This proposition says, suppose F is an ultra closed filter, then given U and V, two open subsets of X, this condition holds. What is this condition? What is this statement? This statement is if and only statement. U union V is inside F if and only if U is inside F or V is inside F. Actually, one way is obvious because F is a filter. Okay. If U is there or V is there, U union V being a superset is there. So what we have to show is that this larger set is there, why the smaller, one of the smaller Sankhya is there. Okay, under the hypothesis that F is a closed filter, ultra closed filter. Okay, so one way is obvious. Next, this implication you have to assume F is an ultra closed filter. U and V are open subsets such that the union is inside F. We have to show one of them is inside F. This is not true means what? Let us examine that. Suppose this is not true, then it follows that the complements UC and VC must be inside F. This is not true means what? Neither U is there nor V is there, but then the complements must be there, because U is an ultra closed filter and we can use the previous theorem. Okay, therefore the union U union V complement, which is nothing but U complement intersection V complement, that must be there. But now you have a problem. We already assumed U union V is inside F, but you are assuming that intersection U intersection V intersection, that is also inside F. This is empty. Okay, it's complement and this one, both of them can't be there. That's all. By a simple induction, we get the following important result. If X is written as a union of finitely many open subsets Vi, and F is an ultra closed filter on X, then one of the Vi's must be in F. Okay, so this is very easy, because what we have proved is that if U and V are open subsets and U union V is inside F, then one of the U and V must be inside F, right? To begin with, every filter contains the entire set X. Therefore, you can just write X as I range from 1 to n minus 1 Vi union Vn. Apply this criteria. Either Vn is there, then we are done, or I range to 1 to n minus 1 Vi must be there inside F. Now you apply induction. Okay, so one of the Vi's must be inside F. All right. So from this one, let us deduce another important result here, which is characterization of compact spaces in terms of ultra closed filters. Remember, in an earlier theorem, we had characterized the compact spaces in terms of ultra filters. Every ultra filter is convergent. That is a condition which ensures that X is compact, and conversely. So exactly same result is now. A space X is compact if and only if every ultra closed filter in it is convergent. Okay. So what is the idea? Let X be a compact space and F be an ultra closed filter in it. Suppose F is not convergent to any point, then you will get a contradiction very easily. Namely, it does not converge to any point means none of this Nx, the neighborhoods, is contained inside F. That is the meaning of that X does not converge to F. This entire neighborhood contained inside F is the same thing as X converges to F. F converges to X. What does this mean? For each point X inside X, we have a neighborhood Vx of X such that this Vx is not in F. One neighborhood for each point. But when you vary these points, you get a covering for X. But now X is compact, so you get a finite covering. Okay, as soon as you have this one, this corollary says that one of the Vi's must be inside F. But that is a contradiction. Just now, none of the Vx is inside F. Okay. So compactness implies that every ultra-closed filter converges to some point. Okay. It may converge to more than one point also. Nobody ensures the uniqueness. Now, let us prove the converse. Assume that every ultra-closed filter on X is convergent. Let C be a family of closed subsets of X with finite intersection property. Okay. We have to show that the entire intersection of members of C is non-empty. So that is enough to show that X is compact, right? So let F be the closed filter generated by C, because any family which has finite intersection property generates a filter, but that will be a closed filter because this will be members of all this here, they are all closed subsets. Okay, so we get a closed filter contained in a ultra closed filter. So let F prime be an ultra closed filter contained inside. That is by John's lemma. Now let be a limit point of this F prime, because we are assuming that every ultra closed filter is convergent. So let X be a limit of F prime. This means that Nx is contained inside F prime. If X is not in C for some C inside C, that would have meant that complement of C is a neighborhood. That complement is a neighborhood. The neighborhood is contained in F prime. That means complement is in F prime. Okay. But all the members of C are inside F and hence inside F prime. Therefore, X must be inside C for every C inside C. That just means that the intersection has the common point X. So that is non-empty. Okay. So characterization of a compact space in terms of ultra closed filters comes out. See, we have to prove this afresh both ways, because if every ultra closed filter is convergent, this does not mean immediately that every ultra filter converges, right? Because there are many more of them. On the other hand, if compact space shows that every ultra filter is convergent, but none of the ultra closed filters may be or maybe a ultra filter, or some of them may be, some of them are not, right? Ultra closed does not mean that it is ultra filter. So either way it is not true, but so we have to prove it fresh. But on the other hand, if you look at the proof, it is not all that different. Of course, this is little harder. We have to use the closedness and generate closed subsets and so on. It's fine. Okay. A non-convergent ultra filter is supposed to indicate the presence of a hole in the space which is making the space non-compact. Okay, because if it were compact, then every ultra closed filter would have been convergent. Okay, so this ultra closed filter, there is no space for it to be convergent, because that point is missing. That is the idea of that there is a missing point in the space. So, and that must be making it non-compact. So this idea is similar to the presence of non-convergent Cauchy sequences in an incomplete metric space. By the very fact, we know that incomplete means, a metric space incomplete means there is a Cauchy sequence which is not convergent. So not convergent Cauchy sequence indicate there are holes inside a metric space. Following a similar track, as in the case of completion of a metric space. We may try to fill up these gaps by including all ultra filters on X. Okay, so that could be one way of looking at it. But then you are warned already by the above theorem that you don't need all ultra filters. If all ultra closed filters are convergent, then the space will be compact. Therefore, it should be possible to get a compactification by just taking care of all the ultra closed filters. So they should be enough to fill up all the holes. So these are all just surmising. I mean, we are just, loud thinking, may say, trying to do. Oh, this may be true. Then finally you have to prove all this. Let us concentrate our attention on the set Wx of all ultra closed filters on X. Okay, let us not give up this idea. That is all right. We have to work, of course. So Wx is nothing but set of all ultra closed filters on X. Okay. Next, going back to the analogy again of completion of a metric space, recall that eventually constant sequences correspond to the points in the space itself, right? If you have some a1, a2, an, and then all an plus 1 etc. are equal to x, that sequence automatically converges to x. And then what will we do in the completion? The element x was identified with this Cauchy sequence, or the other way around, whichever way you want. So that was the map from the space X to the collection of all sequences, and then of course we introduced there some equivalence relation and so on, right? So that was the idea. So we can try to do that, namely, instead of sequences, first of all you have to go to nets. Eventually constant nets is the key word now here. On the other hand, we don't want even nets, but we will use the bridge from nets to the filters which we have defined earlier, right? So what do you get? If S is an eventually constant net, the corresponding Fs, what is that? That will be the singleton atomic filter Fx. Okay, so you see, we are coming to this atomic filter Fx. It is supposed to represent, a prototype of eventually constant sequence. That is the whole idea. Oh, that is how it is convergent also all the time. Okay. In our definition, it is also an ultra closed filter provided X is T1. Till then we don't need that. Okay. All Fx are closed filters if and only if X is a T1 space. That brings us to make a blanket assumption that our space X is a T1 space, because we just don't want to give up this Wx, right, ultra closed filters. So we better assume X is a T1 space before we go further. Okay, in which case all happens is this the subset of all atomic filters will just correspond to the points of X. Okay, so this way Wx can be thought of as a set which contains X by this embedding, by this injective mapping, by this identification X going to Fx. So we have enlarged our space. What remains? We must put some topology on this one so that it becomes compact. That is the first thing. Then we must examine that the map x going to fx is injective, that's okay, continuous, and an embedding, so that the image is dense. This is all we have to do. Okay. Right? It is also clear that each fx converges exactly to one single point. That's very important for us, right? That is an extra bonus though. We were not bothered about that. Okay, but that is because of some strange reason. There is no T1ness or T2ness involved. We don't want to bring the T2ness here. You see, usually a filter will converge to unique point if you have a Hausdorff space. Okay, that is not the reason. These are very special filters fx. They will converge to only one single point. We cannot expect such uniqueness behavior by other ultra filters unless we are ready to make further restriction that x is Hausdorff, right? So therefore it seems that we may need to introduce some kind of equivalence relation on the set Wx. Okay, so that the equivalence classes may be better qualified to become a compactification, just like in the case of completion of metric spaces. Okay, luckily it turns out that we don't have to worry on this point. This process of compactification is much simpler than the construction of a completion of a metric space. That is going to be the topic of discussion for us now, which we shall carry out in the next module. Okay, so this is the motivation for considering the so-called Wallman compactification, as we will do next time. Thank you.